We now take a look at the second of our techniques for finding the particular solution to a non-homogeneous linear differential equation. We've previously looked at the method of undetermined coefficients and all that it entails, but that method is limited in its scope because your function on the right has to be of a specific form, and it's actually a specific and limited form. So when you think about it, just basic exponentials, basic sine and cosine functions, and polynomials, right? There are lots of other functions out there that we would like that could possibly end up in our differential equation, and we need a method for those, right? Now, the full derivation of this method, it's a lengthy process. It's very lengthy, and along the way you have to make several assumptions, and some of those assumptions aren't clear as to why you can make them. If you delve deeper into explaining why you can make those assumptions, it lengthens the process even more. So what I'm going to do, instead of the detailed derivation, I'm essentially going to walk through what the process is, right? It's a nice process, right? It's involved. There's a lot of steps, but it's very procedural. There's no guesswork about this. It's not like when we were working with the method of undetermined coefficients that we had to do kind of an educated guess and possibly modify our guess. Nothing like that. All right, so let's start with the type, essentially the setup for applying this method. And the setup is what we're used to. So I'm going to write down our second order differential equation with the leading coefficient being equal to 1. And that's going to be key in the process, right? And I'm going to use the same notation that we've used several times over. And I think in particular, this was the notation used in our existence and uniqueness theorem, so we're used to this form. So here is our differential equation. And again, notice I am not assuming that the coefficients are constant. This method goes beyond the constant coefficient case, so it's even more general than the ones that we've been solving so far. So given this differential equation, suppose that the complementary function, right, the y sub c, is of this form. So c2, y2. Now, again, I'm not writing the of x, but obviously we know that these are functions of x. The y1 is a function of x, the y2, and so for the yc. So suppose the complementary function is of this form. The method of variation of parameters requires that we look for y sub p of the form. So this is essentially, it's going to give us a formula for y sub p. Now it essentially, it's going to take this form of our complementary function and modify it slightly. It will still be a combination of y1 and y2, which is good because those are the functions in our fundamental set. But instead of having a linear combination of y1 and y2, what we're going to say is we're going to try to construct or build yp in such a way that it can be written in this form. u1, which will be a function of x times y1 plus u2, which also will be a function of x times y2, right? And that's the big thing now, is that we're essentially going to make use of our fundamental set in such a way that we can figure out what y sub p. So we will need to know y1 and y2 in order to generate our y sub p. So obviously the big question is what is U1? What is U2? Well, it turns out that's where it gets messy, right? So I'm going to essentially describe what requirements U1 and U2 would have to satisfy. The trick is, however, we won't have a direct formula for U1 and U2, but instead we're going to have a direct formula for U1 prime and U2 prime. So we'll be able to figure out the derivative of this function and the derivative of this function. And then obviously once you know the derivative, you can work backwards, right? So this is all I will say. And this phrase is meant to summarize, many lines of work. So under certain assumptions, right, it can be shown that the derivatives of U1 and U2 must satisfy the following equations. Or you could say system of equations, because it is going to be a system. So what does it have to satisfy? Well, let me write down the two equations. The first equation is this: U1 prime times Y1 plus U2 prime times Y2, that must be equal to 0, right? So the derivative of this magical function U1 times Y1 plus the derivative of the other magical function U2 times Y2 must be equal to 0. And then the second equation now is this: U1 prime times Y1 prime plus U2 prime times Y2 prime, that must be equal to the function that's on the right-hand side of our nullity, right? When the leading coefficient is 1, right? So once the differential equation is in this form and we identify this function as our f of x goes right there in this system, right? So there we go. So again, what you're not seeing is a lot. Like, how do we come up with these? And again, that's the part that I will do a big hand waving process to say, okay, we're not going into that level of detail. We're not going to get stuck in those weeds, because basically what we want is the process for doing this. It would be absolutely wonderful if you could see every detail that goes into why the process works, but for this particular method, that will take us far afield from where we need to be, right? So let's look at this equation now, or I'm sorry, let's look at the system. And the idea is we need to figure out U1 prime and U2 prime. Now, obviously, because we're solving for functions, it's not quite the linear systems that we're used to, but it does have that form, because if you think about it, here are the unknowns. So here are the unknowns, or one unknown is U1 prime. And then here is another one, right? U2 prime. And it's almost like it is set up like a linear system. And I am going to use Cramer's rule to solve this, because the nice thing about Cramer's rule, like when you have things symbolic like this, Cramer gives us specific formulas to work with, right? So using Cramer's rule, we have the following. So Cramer's rule for a 2 by 2 system, that's what this is. We have two equations and then there are two functions that we're going to solve for. That means we need three determinants. So the first determinant is the determinant of the original coefficients. Now, what are the coefficients? Since the u's are the unknowns, then the y's become the coefficients because I know y1 and I know y2. Those functions make up my fundamental set. So here's the first determinant. So it's going to be y1, y2, and then y1 prime, y2 prime. And if you look closely, think back to the work that we did with the Wronskian of two functions. That's exactly what this is, right? It's the Wronskian of y1 and y2 because look, there are the two functions, they're the derivative of the two functions, and we're taking the determinant of that. For that reason, I am not going to use the letter D for determinant. I'm going to use the letter W for Wronskian. Right, so I'm going to call the determinant of the coefficients, the original coefficients of my system. I'm going to refer to that as W, right? And then Cramer says the second determinant that I need, the one that will allow me to solve for the variable in the first column, I replace these coefficients, right, with the column that's on the right-hand side of the system. So I just need to modify this determinant, and I'm going to call that one W1, right? And instead of having the column y1, y1 prime, we're going to have 0 f of x. So we'll have 0 f of x there. And then the second column stays the same, y2, y2 prime. Right. And then, of course, we need the third and final derivative that will allow us to solve for, in this case, u2 prime. And I'm going to call that one w2. And then, in that case, the first column of our Wronskian stays the same, but then we modify it and replace column 2 with the 0 f of x. So we have y1, y1 prime, and then 0, and then f of x. So there we go, right? So these are the determinants that we need. So I'm not going to evaluate them, right? Because we're essentially just describing the process. But these are three 2 by 2 determinants that we can evaluate. And the nice thing is I'll make a note. Because y1 and y2 form a fundamental set for y sub c, we know that this determinant is never 0, right? So I'll just make a note about that. Since y1 and y2 form a basis, or is a fundamental set, so form a basis for y sub c, we know that this determinant is never 0. What that means is we will always get a unique solution for u1 prime and u2 prime. So hence, a unique solution for u1 prime and u2 prime is guaranteed. So you should always be able to solve these systems, right? Or this system. Okay, so then let's write it down. So here's the formula. So u1 prime, if you remember the pattern for Cramer's rule, so you take the determinant that's modified for that particular variable. So in this case, it's going to be w1. And you divide that by the determinant of the original or coefficients of the original system, so in this case w, and u2 prime will be equal to w2 over w. Then u1 and u2 are found by integrating, right? So u1 and u2 are found by integrating each of these respectively, right? So by integrating each respectively. Now, when we integrate, right, we normally take all possible antiderivatives and, we use that constant of integration. But here we want a particular solution. So for both of these integrals, right, we're going to take the constant of integration to be 0. So for both, because we want a particular function. We don't want a whole set of functions. We want a particular u1 and a particular u2 that can be used to construct our y sub p. So for both, we will take the constant of integration to be 0. So the constant of integration to be 0. All right. And then once we find u1 and u2, then we'll be able to find y sub p. And y sub p is found or constructed. It's almost like we're building this function, is found by using, and then I'll go back and write down. So here's the formula. You're going to take the u1 that we just found and multiply y1 in our fundamental set, and then add to that u2 that we just found and multiply the second function in our fundamental set. And that will be our particular. And we're still going to use our the second version of our superposition principle and taking our y sub c, our complementary function, and adding it to our y sub p, our particular function. All right. So with that in mind, let's do an example to illustrate this particular process. And I'll take a very simple equation. Right. So example. So let's say we have y double prime plus y is equal to the tangent of x. Now, the tangent of x is not a function that we could just, it's not one of our three forms for a method of undetermined coefficients. And the problem with the tangent function is when you repeatedly differentiate them, the tangent function, you don't get, for instance, it doesn't stay just a tangent function. In fact, the first derivative of tangent is secant squared. So it changes form, right? So it's not quite easy. If we think of our differential operator, what would we put into our differential operator to get tangent as the output, right? Not such an easy problem to come up with an educated guess for this y sub p. And this is a perfect example of why the method of variation of parameters is so much more powerful than undetermined coefficients. In fact, you can always use the variation of parameters, but let me warn you, don't make that decision right now. Let's see what goes into this process before you throw out our, method of undetermined coefficients. Because I like that method, but this one, again, sometimes you don't have an option. All right. So first, we are going to find our y sub c, right? So we're going to solve the corresponding homogeneous equation. So that's m squared plus 1 equals 0. Again, you can either use a quadratic formula, or if you're comfortable with the complex numbers, you can see that m in this case is going to be plus or minus I. So this is our third case, and alpha is 0, beta is 1. And then here I'm definitely going to write down the fundamental set so I can see my y1 and my y2, because you see the important role that those functions play in this process, right? So our y1 is going to be e to the alpha x times the cosine of beta x, which simplifies to the cosine of x. And then y2 is e to the alpha x times the sine of beta x. That simplifies to the sine of x, right? So there we go. We have our two functions. Let me go ahead and write down y sub c just so that we have because we're going to need this towards the end. So it's any constant times cosine of x plus any constant times the sine of x. And the other thing that we can make a note of here is that here's our f of x, right? So I'll just say note. And I can write down that this is f of x because the leading coefficient of this differential equation is 1, right? It's 1. So f of x in this particular problem is the tangent of x. So now you don't when you're going through this process, I would say the next big step is to write down. If you can certainly write down the system that u1 prime and u2 prime they have to satisfy. So we know that u1 prime times the cosine of x plus u2 prime times the sine of x, that one has to be equal to 0. And then u1 prime times the derivative of cosine. Now that's going to be negative sine, so I'm going to put it here, negative sine of x. That way when we set up our determinants, we don't forget this negative sign. And then the second term in the second equation is y2 prime times the cosine of x. And that has to be equal to our f of x, which is the tangent function, right? Writing down this particular step is not it's not a key step to where, okay, you have to show this. You could jump right ahead and set up the 3 determinants, right? But I just want to remind you of where those 3 determinants come from, right? So let's write down our w. And w is just going to be our regular Wronskian. So take your y1 and y2 and fill out the first row. So we have cosine of x, sine of x, and then fill out the second row with their derivative. So negative sine of x and cosine of x. And let's just go ahead and compute it as we write them down. So using our AD minus BC formula, we have cosine squared x minus negative sine squared x, and that's cosine squared x plus sine squared x. That's equal to 1. And that's good, right? That's good because, again, having a simple w means that it kind of simplifies the rest of the process. Also note that this is never equal to 0, right? So all that stuff is coming back. Now let's write down W1. So W1, that's where we modify our Wronskian and replace the first column, right? So I'm still using the subscripts that we normally use. I'm just using W as opposed to these. So we're going to replace the first column with the column 0 tangent. So 0 tangent of x, and then the second column stays the same. So we have the sine of x and then the cosine of x. So when we expand this determinant, we're going to get 0 minus the sine of x times the tangent of x. Well, can that be simplified? Not really. I mean, if you write tangent as, I mean, you could do this, for instance. You could write it as negative sine of x times the sine of x over cosine of x, which makes it negative sine squared of x cosine of x. All right. So if you wanted to put it in terms of sine and cosine, that's what it would look like, right? And then our third determinant, W2, now they're 2 by 2. Now the first column is that of the original Wronskian, and then we replace the second column with the column 0 tangent of x. So let's see. So what do we have here? So now we have cosine times tangent minus 0. Now this does simplify, right? Because if I take the cosine of x times the sine of x over the cosine of x, so this reduces to the sine function, all right? Okay, so we have our Wronskians now, so we know that u1 prime is equal to w1 over w. But since w is equal to 1, it means that these things are going to pretty much be the same. So u1 prime is sine squared x over cosine of x, and u2 prime is w2 over w1, which is just the sine of x, all right? So we're inching closer, we're getting there. Next up now, we don't want u1 prime, we need u1, so we have to integrate this. And similarly, we don't want u2 prime, we want u2, so we have to integrate this. So let's start with the harder of the two, right? So u1 will be the integral of negative sine squared x over cosine of x dx. Okay? And what we can do, we can write, so there are different ways you could do this problem. I'm going to show you again, and it kind of goes back to some of those trigonometric integrals that you may have studied previously. But what we can do is we can write the numerator as 1 minus cosine squared. So I'm using that Pythagorean identity and writing sine squared as 1 minus cosine squared. And then this is all over the cosine of x. Well, why am I doing that? Since I have a single term in the denominator, what I can do two things. I can distribute the negative here and switch the signs around, and then I can divide each term by cosine. So let me do it in stages. So if I distribute the negative in the numerator, I'll have cosine squared x minus 1 over the cosine of x dx. Now, if I write this as two separate fractions, cosine squared over cosine minus 1 over cosine, then both of these fractions can be rewritten in a form that I can actually perform the integration, because cosine squared divided by cosine is simply cosine. 1 over cosine is secant. Now, granted, you might not have used the antiderivative of secant as often as the antiderivative of cosine, but again, these are standard results that we established previously in calculus. So the antiderivative of cosine is sine, and the antiderivative of the secant function is the natural log of the absolute value of secant x plus tangent x. And I'll go ahead and put the plus c right now, but again, actually I'm going to put plus c1. But when we actually utilize this, we're going to take the constant of integration here to be 0, right? So let's see. So that's u1, and then u2. In fact, let me write it over here. So u2, that one's a lot easier. It's the integral of the sine function. So it's the integral of the sine of x dx, and that's just negative cosine of x plus c2, right? So taking c1 equals c2 to be 0, we have the following for y sub p. right? And this is what it is. So y sub p, it's going to be so here's u1. So it's going to be the quantity sine of x minus the ln of the absolute value of the secant of x plus the tangent of x, and then that's times our I'm sorry, this is not y2, this is y sub p. So this is my u1, and this is to multiply y1. y1 in this case is the cosine of x, right? And then add to that u2, which is negative cosine of x, times y2, which is our sine function. Right, so I'll do that. There we go. So if let's see, if sometimes the y sub p can be simplified quite a bit. Let's see what happens. Let's say if I distribute the cosine, I'll have the sine of x times the cosine of x minus, I'll put the cosine in front of the ln. Right, so not much going on there. But then over here, what do I have? I have minus the cosine of x, the sine of x. So this product, right, is the negative of this product. So they cancel out. So our y sub p, it's not, certainly when I look at it now, I'm thinking there's absolutely no way I would have guessed this as, you know, what the input to my differential operator would be in order to get tangent as the output. Just no way you would guess this. And in some sense, it's kind of, you know, what it's like when you get to those advanced techniques in integration, where you can't really, when you get to the final answer, you're like, okay, we got it. But it's not something that was readily apparent, right? It was just a little too involved. Right? So that's for y sub p. And then finally, so the general solution, of the dE is, so again, we're still using our superposition principle, so it's y sub c plus y sub p. So remember, y sub c, that is c1 cosine of x plus c2 sine of x, and then now we get to add this term, but since it has a negative coefficient, I'm just going to write it as minus cosine of x times the natural log of the absolute value of secant x plus the tangent of x, right? And that's our solution. So that illustrates the variation of parameters method. Again, it's provided that the calculus doesn't get too messy. I mean, the linear algebra part usually goes pretty well using Cramer's, provided the antiderivative doesn't get too messy. It's a fairly straightforward process, but you can see it relies a little bit more on the advanced, linear algebra and advanced sometimes integration techniques, as opposed to the method of undetermined coefficients, where you're making an educated guess. And you have to use some derivatives and some algebra, but it's not quite as technical as the variation of parameters. So, but essentially you have your choice, right? You can pick your poison, pick your fruit, whatever it is. Either way, we now have two techniques that we can use to find our particular function and then solve our non-homogeneous equations. See you in the next video.